Hello, my girls, and welcome to your first summer science lesson. Hopefully you don't think that I forgot about you. I did not forget about you. I've just had a lot going on in my personal life that's made it a little bit difficult for me to make the videos. And also, I really wanted to leave some time with everything that's happening in our world right now. With George Floyd and racism, which is very prevalent in our country, unfortunately. So I really wanted to leave the space of, last weekend and this week to, not try to take over with biology stuff, but let you take in the information right now with the Black Lives Matter movement. But also don't want to leave you hanging, so here is your first official summer science lesson. So it's going to be a little bit different. I'm probably not going to give you guys too many worksheets or anything. I'll put some resources up on OneNote that you're still a part of that you can then work on there, and then you can shoot me an email if you do the worksheet, and I'll go in and check it to see if you're actually understanding what's going on. But please understand that all this stuff is obviously optional. It's just fun stuff to continue learning since you guys kind of got shortchanged this year. So we're going to talk about pedigrees, which are basically a tool that geneticists use to trace family histories of different diseases that run in families or different traits that run in families. So if you look to the pictures on the right, those are all alternative forms of human characters. So whether someone has freckles or doesn't have freckles, whether someone has the widow's peak or not, and whether they have free or attached earlobes. I don't think this picture does the best justice to the free or attached, but if you look, I have attached earlobes, but if you look, some people, maybe someone in your family, they have what looks like a crease or a line right here, that their earlobe, the bottom of their earlobe is not attached to the skin of their face. But all of these traits that you're seeing to the right are going to follow simple Mendelian genetics like we talked about before school let out. So this is all things that are controlled by simple dominant and recessive traits. There's no polygenetic things where there's multiple genes. We'll talk about that a little bit later. This is just one gene, one protein that causes a particular effect. In this case, we're looking at, again, freckles, hairline, or earlobe attachment. And I think I had mentioned this one time in one of the Zoom calls that we did, but in genetics, the word dominant does not always imply that it is A, good, or B, more common. It could be bad, and it could be uncommon, and I'll give you guys some examples of that in the next couple of slides. But the thing that you see more often is actually called the wild type. It's not like dominant is more and recessive is less, or dominant is better and recessive is worse. That's not the case. The wild type is what you're going to see the most dominantly in nature. So if you look around, what do most people have? That's the wild type. And it works like that for other animals too. It's not just humans, but I like to talk about humans when we do genetics because we're human and it's fun, so we're going to talk about it. Just one example is that recessive traits being more common. I think I told you guys about the pointed cat ears versus the curved cat ears, and how curved are actually the dominant trait and pointy are the recessive trait. But also freckles. So having no freckles is way more common if you look around. However, freckles are a recessive trait, or they're a dominant trait. So you would expect, if dominant means more common, you would expect to see more people with freckles, but you don't. You see less people with freckles, despite all of the YouTube beauty influencers who now draw freckles on their face. Most people don't have freckles, and that is actually recessive. So if two people that don't have freckles have a kid, their kid probably will not have freckles. It's a little bit difficult to say, because you can get freckles from sun exposure to a certain extent, but overall having freckles or not is going to be a genetic trait. Oh, sorry, that was kind of confusing. My bad. Okay, so pedigrees come into play when people start thinking about like having kids, and is there a family history of a certain disease on either side of the family? Is there something that they need to, be worried about? Obviously, you can't do test crosses on humans like you can do with animals and plants. I think one of the questions I put on your exam, which I ended up throwing out, but I put in just to see if anyone would kind of understand and like kind of think further than what I had taught. A couple people got it right, but not many. Like I said, I threw it out. But the question was asking you if you wanted to determine an unknown genotype of a plant, what type of plant would you have to cross it against to know what that unknown's genotype is? You'd have to cross it with something that has all recessive traits. That way, if you end up seeing the dominant trait, you know that that unknown genotype at least had to carry that dominant trait somewhere, if that's what you saw. So you can determine if they're heterozygote or if they're homozygous dominant from doing test crosses. But anyway, with humans, you can't do a test cross because you can't be like, hey, Susie, you're going to have a kid with Brad right now, and we're going to tell you to do it. But Susie doesn't like Brad, and Brad doesn't like Susie, and they definitely don't want to have a kid together, right? So you can't do test cross on humans because you can't tell humans who to mate with, and you can't tell them when to mate with someone, and you can't tell them how many kids they're going to have. That's like super unethical, crosses all kinds of boundaries. So what geneticists have to do instead is they have to go back and use the family history, and so they'll go talk to family members like, hey, did this family member have such and such? Was this family member colorblind? Did this family member have a widow's peak? Whatever. And they can build these big pedigrees, which are basically, I'll show you on the next slide, they're like these little puzzles that are shaded and have different shapes to help you determine if a certain family member had a certain disease or a certain trait or not. So here we go. So to analyze the pedigree, the geneticist will apply the same Mendelian laws and logic that we know without really doing Punnett squares. You could do Punnett squares, but you don't necessarily have to do Punnett squares when you're looking at a pedigree. And so in this pedigree on the right, you are looking at whether the earlobes are attached or not. The recessive allele, the lowercase f in this case, is an attached earlobe. So like what I have would be attached. That means I have two recessive alleles. I have two lowercase f's in my alleles, in my genes. That's why I have attached earlobes. And then the uppercase F, or the dominant allele, is a free earlobe where it's not attached. So when you're looking at a pedigree, it's always the same, okay? The top row, that's going to be the oldest generation for which we have information. So in this case, this would be like your grandparents. And these can get really big. If you have information on great-grandparents and great-great-grandparents, you can add that too. As of right now, like with our technology and like our record keeping, we don't really go far. We don't really have information that far back unless our family was like really good at keeping records and books and stuff. But I think in the coming years, in coming generations, with all of the technology we have now, like my great-great-great-grandchildren will definitely be able to learn about the traits that I had because of our computers' abilities to take pictures and talk to each other and stuff like that. Obviously, it's much better. But for the most part, pedigrees will typically show like the grandparents. Sometimes they know information about the great-grandparents, but it's not very often. But anyway, so the topmost first row always shows you the oldest generation for which we have information. And then the next row would be their kids, so that'd be like your parents. And then the next row would be their kids, so like you and I, right? So grandparents, parents, us. And then the squares are always going to indicate the males, and the circles are always going to indicate females. Even if you don't have a key, like you see right here, that's always the same. The squares are always males, and the circles are always females. Now, if you see, and they won't always put the genotype. In fact, they normally don't put the genotype. That's just here as a teaching tool for you. You're looking to see which boxes or circles are shaded. If a box is shaded in, or if a circle is shaded in, I'm kind of trying to point with my stylus over there if you see my eyes going crazy. But the shaded in means that the person shows the trait that you're looking for. In this case, we're looking to see if they have attached earlobes. So if the earlobes are attached, since that's a recessive trait, if they are attached, then their boxes are going to be shaded, which automatically means that they are homozygous recessive. Some other things whenever you are looking at a pedigree, the lines in between squares and circles like this, that shows a marriage. So these people got married, right? And then this line extending off of them down the center, that's leading to all of their children. Same thing here. So this person married this person, and then they had these 2 kids, right? And then these people got married, and they had these 4 children. And then this son from this family and this daughter from this family got married, and now they have these kids. Okay, so that's what those lines indicate. Technically, it doesn't always indicate marriage because people have kids out of wedlock all the time. I guess more so I should say that a connecting line like that is going to show you that those people had an offspring to each other. Not to each other, with each other. To each other sounds weird. They had an offspring with each other. And so some other things about a pedigree that you see less often, but I always get asked about, is like, what if somebody has identical twins? Well, if somebody has twins, then instead of like having these straight lines right here, if you have a pair of twins, they end up looking like this. They come off from like the same point. So let's say you had twin girls. It would look like that. So they're instead of having their own individual line, they both come from the same point. So, you know, if you ever see that, that's twins. Also, there is one example that I am going to have on one of the worksheets just to see if you can like figure out the puzzle of a pedigree. There is one, you probably will notice it, but I accidentally married siblings and had them have children. Pretend like I didn't do that, okay? I am aware that that's horrifying, but it's like already in there. And I mean, I didn't make it, somebody else made it, and I just borrowed it / stole it, but I'm not going to fix it. So just, you can still answer all the questions, but when you're like, oh my god, incest, oh, Miss Ringswald, I didn't mean to, okay, but it is there, so you might notice it. I'm not going to tell you which one, see if you find it, but obviously I did not mean to have siblings marry each other. It's very weird. Okay, so it looks like I have only like a few minutes left on this one, so I'm going to cut it here and then have another one right behind it. I'm going to try not to do too many because this is supposed to be fun, so I don't want to like bore you with hours of videos, but I do want you to get some more knowledge, so yeah, you'll have probably maybe 1.5 after this one. Fingers crossed. That's only 1.5. Please give me feedback on if you like this or not, so that I can know to do things differently if I need to or whatever. Okay, yeah, bye!